Morning, everyone. I am Sehun from Christ, and today I will present about my work, which is titled Parallelizing Picard Iterations. Actually, from ERC, one of the main topic is about function calculus, which includes the Riemann sum and other function calculus. From this presentation, I will try to parallelize the Riemann sum by using the disputation techniques and the prefix sum, and finally the Riemann sum. Yes. This presentation contains of 7 parts, which are motivation and benchmark problems and theoretical complexity and technology and experiment results, finally conclusion and future works. Now let's look at motivation. ERC represents for exact real computation. Currently, from current my research, I found that ERC currently successfully implemented for single numbers, which includes matrices and polynomials. After successfully implementing the ERC for single numbers, the next step is actually for implementing the function calculus. The function calculus for ERC is difficult because while implementing the ERC at function calculus, it contains exponentially more information than real numbers. Additionally, approximating a function requires a very many sample points, which we'll show in the next slide. Finally, key operations such as integration and differentiation is computationally expensive. Example of comparison between ERC at the single number and ERC at the function. As you can see in the left slide, while implementing a single real number x, which is in the domain between -1 and 1, you can see that it only needs one sample point. In comparison, while we are trying to implement the function which is from the unit interval into -1 interval, which is -1 to 1, it needs the various sample points. Here is the actual comparison between the real number and the function. As you can see in the previous, for the approximation, it up to the error 2 to the power of -n, it only needs n plus 1 bits, with 1 bit is needed to care about the. Now let's look at the relation between the Riemann sum and prefix sum. As you have learned in the high school or the first year of the undergraduate school, we can find that the Riemann sum can be written in the left slide. And without the notation is actually written in the left slide. When we make the O interval inequivalent and choose the O samples which O difference is equivalent, then we can find that the left notation can be changed to the right notation, and this can be thought as a prefix sum. From the optimal situation, we can find that the sequential prefix sums takes O and runtime. In comparison, parallel prefix sum takes O log large and runtime, which is actually O and depth. Any questions until here? Now let's look at the benchmark problem. The benchmark I have used as a two concrete benchmark problem, which is exponential Picard iteration and logistic Picard iteration. After looking at the two Picard iteration, I will explain the third Picard iteration, which is generic Picard iteration, which takes for the most of the given differential equation. Now let's first look at exponential Picard iteration. The goal of the Picard iteration is to solve the below Picard iteration, which is given in the slide. Actually, because this is the theoretical solution of the above the single equation. As you can know, the solution of this equation is well known. So while doing the experiment, we can actually test whether the given code is working well. Finally, we can, by using the discretization, we can write the above the equation into the below equation, and actually we can actually also find that above equation is also the integral version of the equation. Now let's look at the logistic equation. Actually, logistic equation actually also follows the same version, except the fact that the differentiation term is not nonlinear. Oh, may I pause for a second? Sorry. May I pause for a second? Coil iteration, which has the form of derivative of ut is actually to f, which is in f to u to t. So we are actually, our main goal is trying to find when there's no restriction, except the derivative is only related to ut, then we are actually trying to solve the actual form. While solving this equation, we can find that the ut is the fixed point of the below equation. We can change to the given form into the discretization, which is the given when L is larger than 0, which is promised to the restrict concept to F, and when the samples are given, then we can actually return the samples of U solution, which is look like here. Any questions until here? Here is the time complexity of Picard iteration. Unfortunately, unlike the optimal situation, I actually failed to try the optimal algorithm which uses the O log and pedal time. So I use the simple pedal time which divides all of the samples into the p samples, p intervals, and actually calculate the p times into. So here is the actual result of the actual theoretical estimate of the result. Any questions on here? Now let's look at the technology. For this experiment, I used the two technology, which is multi-core CPU and GPU. For multi-core CPU can use for a small number of workers. However, its overhead and overload is small. In comparison, GPU can use very many workers or cores. However, it has a large of overhead. So I use these two technology to compare what happens if overload is large and what happens if there is many workers. For the experimental setup, I have used the few inputs which are given in the slide, which are size of the output array and number of threads, and finally functions which represent the derivative solution function. For output, it returns the maximum error and finally the runtime of the code. Yeah. Here are the results for the experiment. First, I have first experiment for the n equals 2 to the 20, which is small enough. As you can see in the slide, when p is small enough, then the experiment result follows the experiment result follows the theory. In comparison, when p is too large, you can find that overload actually exceeds the improvement which is taken by parallel optimization, so the runtime actually becomes increases. When n is large enough, in this case, when n is equals to 2 to the 26, we can find that although the workers become larger and larger, we can find that time becomes smaller and smaller. However, as the p becomes larger, the the experiment results doesn't follow the theory as you can see at this brown line. In conclusion, function level ERC requires exponentially many samples, so sequential computation becomes expensive. And because iterationally networks contains repeat integrations, which by using few discretizations and few assumptions can be approximating using prefix sums. Finally, experimentation shows parallel prefix sums are beneficial for large sample sizes, while overhead dominance for small sample sizes. My next goal is to add implementation of function calculi at item package, which includes the piecewise iteration and function type and other types of function operations. Thanks for listening my presentation.